I'd like to introduce our next presentation on fungicide resistance. This will be presented by Olga Kozar from WSU, also contributed Tobin Peaver. This presentation, the series of presentations will also have pesticide recertification credit, and I'll have those forms up later in the hour.
Go ahead, Olga.
Thank you. Hello. Good afternoon, everyone. So today I'm going to tell you what we've learned about resistance of Botrytis, a causal agent of gray mold, on small fruit crops in Pacific Northwest to frag group 7 fungicides. So frag group 7 fungicides, they also called succinate dehydrogenase inhibitors, or SDHIs. These fungicides target a specific molecule enzyme in a fungal cell that is called succinate dehydrogenase in mitochondria of a fungal cell. And this way, they disrupt the respiration system of the fungus. So fungus dies because it cannot produce energy anymore. One of the fungicides that belong to this group is called fungicide pristine with active ingredient boscolid, is widely used for gray mold control in berries in Pacific Northwest. And it has been used for many years after it was registered. We also know that there is widespread resistance to pristine in Botrytis populations in Pacific Northwest developed because of pretty frequent usage of the chemical. And when I say widespread resistance, I refer to our data that we collected from, first we collected Botrytis strains from 29 fields of different small fruit crops in Washington. Here on the map, you can see the schematic representation of our sampling. So we sampled three counties, Whatcom, Skagit, Island. And we sampled 29 fields on 9 different farms. So each of the circles here represents a field of different small fruit crop that you can see a legend here based on a color coding. And each of the rectangular here represents a farm. So we sampled multiple fields of different crops on few farms. When we screened this about 700 Botrytis strains total for resistance to pristine, and now you can see the data with pie charts for each of the fields with resistance profiles. Brown area represents the amount of strains or percentage of strains that were resistant to pristine, and gray area represents the percentage of strains that were sensitive to pristine. So first of all, we see, as I just said before, widespread resistance to pristine in Botrytis populations. And we also can see that the resistance frequencies differ significantly between different farms and also between different fields on the same farm. But there is a lot of resistance to pristine that makes this fungicide ineffective in order to control gray mold on berries. This frag group 7 fungicides and our boscolid, so based on our estimations, about 70% of Botrytis strains in berries in Washington are resistant to pristine. A couple years ago, chemical companies developed 5 new different frag group 7 fungicides that are listed here: Kenja, Depedin, Luna, Fontelis, and Xemium. 2 of them, Kenja and Luna, that are highlighted in red, I believe are registered in Washington for control of gray mold, while others are not. When we think about fungicides from the same frag group, it means that they have the same mode of action. So they target the same enzyme in a mitochondria of a fungus. And when we think about resistance and different fungicides from the same frag group, we usually expect that if fungus developed resistance to one of the fungicides from the same frag group, we expect that other fungicides from the same frag group will be not effective in controlling this fungus. So there is going to be a patterns of cross-resistance. And here is just an example to show you what I'm talking about. So here is our data on correlation of sensitivities to two fungicides from different frag group 9, ciprodenyl and perimethanol. Both of them belong to frag group 9. We screened some Botrytis strains on ciprodenyl resistance, and then we screened the same Botrytis strains on perimethanol resistance. And on this graph, you can clearly see what we call a typical pattern of cross-resistance within the same frag group. The isolates or strains, Botrytis strains that were sensitive to ciprodenyl were also sensitive to perimethanol, while the Botrytis strains that were resistant to ciprodenyl are also resistant to perimethanol. So that's what we usually expect to see with fungicide from the same frag group. When we come back to our frag group 7 fungicides and these 5 new chemicals that were developed by companies a couple years ago, what is unique about these fungicides is that the patterns of cross-resistance are different in this case. So here you can see 5 different graphs with cross-resistance patterns of boscolid or pristine and other new frag 7 fungicides. So our pristine is on the x-axis on each of the graphs, and each of the new chemicals, new fungicides, on the y-axis. When we just look at all these 5 graphs, we can see that they clearly fall into 2 different groups. Group number 1, where we see the relationship between resistance to pristine and Luna or Kenja, slightly negative cross-resistance, meaning that resistant to boscolid or to pristine Botrytis strains show increased sensitivity to these two new chemicals, while the patterns of cross-resistance between pristine and adapidine, xemium, and Fontelis follow positive correlation. So we clearly see 2 different groups how this new frag group 7 fungicides behave when we screen them on Botrytis strains resistant to pristine. So this frag group 7 fungicides, we know that, so these new fungicides are claimed by their manufacturers to control some of the boscolid resistant strains of Botrytis. We also know the molecular mechanism of boscolid resistance. So we know where exactly the mutation happens in what gene, and we can easily detect it in the lab. So we know where to look in order to see the mechanism of resistance. And we also know that efficacy of these new fungicides will depend on what type of mutation is present in Botrytis in Pacific Northwest. When I talk about mutations, so let's look at this table here. There have been reported 6 different mutations in the Botrytis genome in a fungus that cause resistance to boscolid. So our frag group 7 fungicides in columns, and each of the mutations in rows. And here we can see cross-resistance patterns in them. For example, the first mutation, H272R, it causes resistance to boscolid, but it is expected that other fungicides will be effective for the fungus that carry this mutation. Another example with mutation H272Y that again causes resistance to boscolid, but it is expected that this Botrytis strain that carries this mutation is supposed to be controlled by Kenja and Luna, but there is expected cross-resistance with xemium and Fontelis, and so on. And the third one, for example, H272V mutation, it causes resistance to boscolid, but it also expected to cause cross-resistance to all these new frag group 7 fungicides. When we did our analysis of pristine resistance, and then when we identified what types of mutation cause this resistance in our populations, we found out that in 40% Botrytis strains that are resistant to pristine carry mutation H272R. 60% of Botrytis strains that are resistant to pristine carry mutation H272Y. And only one isolate was detected with mutation H272V, which causes cross-resistance for all the fungicides. When we come back to our map with our pristine resistance data, and when we overlay our mutation data on here, so now you can see each of the pie charts shows not just the percentage of Botrytis strains that were resistant to pristine, but also the percentage of strains that carried one or another mutation. As I just said, two most common mutations were identified in Washington, H272Y and H272R. Here we can see that both mutations are often present within the same field, but we also see different ratios of the two mutations in each of the fields. I also want to mention that if you look closer, for example, on this farm with 5 different fields that we sampled, we see different resistance profiles even in neighboring fields. What it means? It means that Botrytis doesn't seem to move very far, even within the same farm. So this population stay pretty local within the field. So we know what kind of mutations are present mostly in Pacific Northwest in Washington. We took these isolates, Botrytis isolates, and we screened them on new frag group 7 fungicides. Here you can see the results of this analysis. So we have our 4 frag group 7 fungicides on the x-axis, and the resistance value, EC50 value, which is standardized measure of resistance, on the y-axis. And since we knew what mutation is present in what strain, we were able to separate them by mutations too. Let's look at fluxopyroxide or Xemium fungicide. We see that in this case, the Botrytis strains that carried H272Y mutation, black bar, had EC50 value almost 10 on average, while Botrytis strains that carried H272R mutation, red bar, their EC50 value was much lower, about 2. And similar story with penthiopyrite, much higher resistance value in Y mutation, in strains that carried Y mutation compared to EC50 value of strains that carried R mutation. When we look at these results, it's still, we don't know whether these strains will be controlled by field rates of fungicides. So we don't know where is the threshold of resistance, what is the true resistance? Is the threshold somewhere here, or is the threshold somewhere higher? In order to answer this question, we performed fruit assays. We took some raspberry fruit, we treated the fruit with each of these different chemicals, and then inoculated this fruit with Botrytis strains that carried either Y or R mutation with different EC50 values, in order to see at what point the fungicide will not be able to control Botrytis anymore. Here is an example of such experiment. So this is a fruit assay with field rates of Xemium as an example. So what we did, we took raspberry fruit, and half of this fruit we sprayed with field rates of the fungicide Xemium, while the other half was left without any fungicide treated, our control. And then we inoculated each of these rows of raspberries with different Botrytis strain, because the first one was sensitive, so didn't have any mutation. Then we had few different isolates that carried either R or Y mutation with different EC50 values. And with time progression, you can see here, after 48 hours, we already start seeing some mold development on our fruit that was not protected with fungicide. And again, after 72 hours, we start seeing some infection on fruit that was also protected with fungicide. If you look at this photo more closely, we can see that infection happened on protected fruit only on ones that were infected with Botrytis strains that carried HU72Y mutation with different EC50 values. So only these isolates were able to cause infection on fungicide-protected fruit, while the sensitive and the isolate that carried HU72R mutation didn't cause infection on red raspberry. You can see some green dots in here. I just want to mention that this is not botrytis. This is just a contamination by another fungus, Cladosporium, but there was no botrytis symptoms on these berries at all. If we come back briefly to our graphs that we just talked about with EC50 values, in case of our Xemium or fluxapyroxide, and if we ask our question again, so where is this threshold for resistance for this specific fungicide? Based on this data, on fruit data, now we can say that the threshold value is probably somewhere around here, because all the strains that carried HU72R mutation, red bar, with different EC50 values were inhibited by the fungicide, while the strains that carried Y mutation were able to cause the infection. And we did such experiments with fruit for other fungicides as well. So here is a summary of our fruit assays with Xemium. So when we inoculated fruit with strains that carried HU72R mutation, it was completely inhibited. But 65% of fruit that was infected with HU72Y mutation had symptoms of gray mold on them. Here we can see the results for Funtalis, or active ingredient pentylpyrite fungicide. Again, when a fruit was inoculated with Botrytis strain that carried HU72Y mutation, or black bar, more than 70% of fruit had infection on them. And about 40% of fruit that was infected with isolate carrying HU72R mutation also had rot on them. So there was no incomplete control of HU72R isolate by Funtalis. With fluopyrum, for example, when we treated fruit with fluopyrum and inoculated either with HU72R or Y isolates, fluopyrum was able to control both of them, meaning that fluopyrum seems to be effective against botrytis that carries either HU72R or Y mutation. We are still working on data for Kenja and adapidine. We don't have a fruit data yet, but that's what we are doing right now in a lab. We will have it soon. So if we come back to our resistance and EC50 values for each of these fungicides, and if we come back to our question, so where is the threshold for these fungicides in resistance? Now, having this fruit data, we can say that threshold is probably somewhere here, because again, Xemium was able to control strains with R mutation, but not Y, as well as Funtalis, and there was a partial control of strains with R mutation by Funtalis. So, as a result, we've learned that mutations that confer resistance to all new FRAC7 fungicides, such as the V mutations that I showed you in the beginning, are extremely rare in Pacific Northwest at the present time. And this is very good news because such mutations cause cross-resistance to all new FRAC7 fungicides. And if population had such mutations in berry fields, we probably wouldn't be able to use any of these fungicides. R mutation, which is present in 40% Botrytis strains in Pacific Northwest, confers sensitivity to Xemium and Luna, and also likely Kenja, but that's something that we still need to test in a lab. Y mutation that confers 60% Botrytis strains in Pacific Northwest on berries confers sensitivity to Luna only. And also it confers resistance to Xemium and Funtalis, and also likely adapidine. But again, adapidine needs to be tested in a lab. In order to predict effectiveness of these new FRAC7 fungicides, we need to know which mutation is present in which field, because if you remember, I said at the beginning that our populations seem to be pretty local, and resistance profiles differ between fields even on the same farm. So in order to do that, there is a need to develop a cheap and fast method for screening individual fields, and that we would be able to give this information to growers. And that would be logical next steps in this work. With that, I'll be happy to take any questions. Thank you.
Thank you. Are there any questions for Olga? Olga, thank you.
Yeah, thank you so much.
Our next presentation is Justin O'Day, a regional ag specialist for WSU. He'll be presenting on rose stem girdler, an emerging pest of caneberries in the Pacific Northwest. And is this also a remote? And this will also be a remote presentation.
Can everybody see this and hear me?
Yep, we got you, Justin.
Great.